Hi everyone. So welcome to supplementary video 5. And this video is basically about the discussion of approximately 1D problems. And the specific case that we'll be focusing on is the case where a 2D problem is reduced to a 1D problem through an approximation. So we discussed the series resistance approximation in lecture. And I just wanted to first quickly recap what we had discussed in the lecture. And then what I want to do basically in this video is give you a few more examples so that you can better appreciate the difference between different scenarios that may arrive where you can basically approximate a 2D problem into a 1D problem. Okay, so let's just quickly see what the problem what we discussed in class was. So we discussed in class the problem where there was a conductive slab of thermal conductivity K, right? And what we were told was that the length of the slab is L and the width is 2W. So the X direction, which is the direction of the width, goes from minus W to W, and the Z goes from 0 to L. We were also told that the boundary that I'm shading here, which is at at Z equal to 0, the temperature is kept constant at T0, and all the remaining sites are essentially exposed to air, which has an ambient temperature of T infinity and a heat transfer coefficient of H. Okay, so this was a problem. We were said this is a 2D problem, and we were asked to solve this problem. And the condition that we were given was that HW by K is much smaller than 1, right? We were asked to basically solve this problem. So what we did as a first step was we wrote the governing equation, and we started with the equation and said because it's unsteady, there is no flow, there is no heat generation. This will simply become del square T by del x square plus del square T by del z square is equal to 0. And because there is an x square and a z square in the denominator, we need two boundary conditions in x and two boundary conditions in z, right? So we said that simply that del t by del x at x is equal to 0 is 0 because of symmetry. So I hope you remember this from the lecture that this plane here x is equal to 0. There is symmetry about this plane because you cannot differentiate between whether it's the top portion or the bottom portion. It's basically the same. You can reverse them and the problem will still remain the same. Then the second thing which we did was the interfacial balance at x is equal to W, where this was equal to HT minus T infinity, because this is the flux in the inside the slab, and this is the flux outside, which is in the air, and this is the interfacial balance. This is the two boundary conditions in X. Then we did a boundary condition in Z, so I'm going to the left. Just to remind you that at Tx comma Z equal to 0, we said this is T naught, and then fourth was again the same as the other surfaces, that at Z equal to L, this is equal to HT minus T infinity. Right. So just to quickly again show you, we started with the governing equation, and we derived the four boundary. We first wrote the governing equation, then we derived the boundary conditions: 2 in X, 2 in Z. One is symmetry, one is interfacial balance, and one is constant temperature, and again in Z there is interfacial balance. Okay, so this is what we did. Then we said, okay, now it's a 2D problem. We don't really know how to solve this problem. So what we did was we said we'll use something known as the order of magnitude analysis on the second boundary condition. And I'm not going to elaborate much on this point. I'll just simply say that from this, and you can again go back and check in the lecture, we said that Tx comma Z can simply be approximated as T bar of Z. Okay, and this comes out because what we said was that the temperature drop outside the conductive slab is much larger than inside the conductive slab, and that's because essentially this means that the air resistance is much larger than the slab resistance, because slab has a much larger conductivity, so it has a much less resistance, and because it has a much less resistance, the temperature drop is essentially can be ignored. Okay, now if we did that, then we did a shell balance, to arrive at the to arrive at the equation k del k d square t by dz square t bar by dz square is h into t bar minus t infinity, and at t bar at z equal to 0 is t naught, and minus k dt bar by dz at z equal to L is h into t bar minus t infinity. Okay, so we discussed this problem, and I wanted to do the full recap, of how we got there, because we basically converted from a 2D problem into a 1D problem, and we used an order of magnitude analysis and a shell balance. Now, what I want to do next, and I will not go into too much detail now, but basically what I will do is describe few scenarios, and then I want to compare and contrast with this scenario. Okay, so let's do scenario two. So the first one we discussed now was scenario one. Let's discuss scenario two. Scenario two. Okay, so what we have been told is that the problem remains the same, but we have basically insulated these two sides. We have insulated this side, and we have insulated this side. Instead of being exposed to air, this side is still exposed to air with heat transfer coefficient H and ambient temperature T infinity. Okay, so this is still exposed, but the top and bottom once we have insulated. So what will happen in this scenario? So that's the first thing we want to discuss. Now this is also a 2D problem, right? This is X, sorry, this is Z and this is X. So we'll have the same governing equation, which is del square T by del X square plus del square T by del Z square is equal to 0, right? Del square T by del X square plus del square T by del Z square equal to 0. So this is the first step will remain the same, which is the same governing equation, steady and 2D, but the boundary conditions are not different. So what are the boundary conditions? So in X, we know that del T by del X is now 0. It will still be 0 at 0 because of symmetry, right? But then it will also be 0 now at X is equal to W, because basically it's insulated, right? Insulation. So insulation means that there cannot be any flux. So this is 0, and then the other two boundary conditions remain the same, that at X Z is equal to 0 remains T naught and minus K del T by del Z at Z equal to L is H into T minus T infinity, right? Now, the problem is the same, but the boundary conditions, the governing equation is the same, but now the boundary conditions have changed. In essence, the main boundary conditions that has changed is this one, right? Now there is no flux even at X is equal to W. Now this begs the question that if there is no flux at X is equal to 0, there is no flux at X is equal to W in the X direction, then should there be any X dependence at all, right? And the answer is that if there is no flux going in either of the direction, there is no generation of heat, right? So there is no reason for the temperature to have any dependence at all. And it is in fact true that the temperature can actually be exactly written as T of x comma z. T of x comma z will exactly be T of z in this case, no X dependence. So this is a 2D geometry, but because of the fact that there is no flux in the other direction, in the X direction, it basically becomes an exactly 1D problem. So now you might say, well, we said this is a 1D problem. This is exactly 1D problem, and this is approximately 1D problem. So is there any difference at all? And to do that, what I want to do is essentially show you that there is a difference between the two problems. So what we can do is, let's go back here, del square T by del X square plus del square T by del Z square is equal to 0. Okay, now what I wanted to say is let's integrate the problem. Okay, so let's integrate this equation with x. And we want to do that because we know the fluxes at two different conditions. So let's say we did del square T by del x square dx, and we did 0 to w del square T by del Z square dx 0 to w is also equal to 0, right? We integrate the equation with x. Now the point is this becomes del T by del x 0 to w, and here because t is not a function of x, this simply becomes w del square T by del Z square, or rather d square T by uh, uh, yeah, I mean this will become clear because this only x dependent is 0, right? Now because the derivative is 0 in both directions, this is exactly equal to 0 because we know dt by dx is 0, del t by del x is 0 here, del t by del x is 0 here. So this means it's 0. So my governing equation now actually becomes d square t by d square is equal to 0, which makes sense essentially because there is no dependence in the x direction, and the boundary conditions here are t equal to t naught at z equal to 0 and minus k dt by dz at z equal to L is h into t minus t infinity. So we went through this exercise because see that there is a difference between this problem and the approximately 1D problem is that our governing equation is different, even though the boundary conditions are the same, right? So there is a difference. The fact that there is no flux going out makes it exactly 1D, whereas this problem was approximately 1D, okay? And it was approximately 1D because we said that HW by K is much smaller than 1, okay? Now, so I hope this makes sense. In this scenario, we said it's exactly 1D because there is no flux in the x direction anywhere. So that means we can and we can also integrate and get the equation, which is the same equation that we will expect if t was only a function of x uh, and only a function of z, and the boundary conditions remain the same in the z direction. Now let's do a third scenario, scenario 3, where we have again the same problem. We have the same problem here. But rather than insulation, we say constant flux Q. Constant flux Q. Okay, we say that this is true. Constant flux Q on both sides. But this side is still exposed to air, H at T infinity. This side is still the same. Now again, this first step would be the same, which is del square T by del x square plus del square T by del Z square is equal to 0. But my boundary conditions will be slightly different now. We will have del T by del x at x is equal to 0 is 0, symmetry again. But the second boundary condition will be now minus del T by del x at x is equal to w is Q, right? And this is the constant flux, which has been given to us, constant flux. And the other equation, other boundary conditions remains the same. At z equal to 0 is T naught and minus k del T by del z. At z equal to L is h of T minus T infinity. This is the interfacial balance. Okay. Now, so this is again a 2D problem, and that their boundary conditions are different. Now, in this problem, because this flux is constant, right, we do see that there is some opportunity that we can actually still do something interesting. And the reason to do that is because you see when we do this integration, we saw that we got a flux or a derivative term with respect to x out, and we know that the derivatives here are actually constant. So can we utilize something of that nature? So we can. So for that, we will define something known as T bar, which is the average temperature, much like the first problem we were discussing, scenario 1. I'll come back to that again. So let's just describe this as 0 to W by W. Okay, this is basically saying Let's average out the temperature in the x direction. And this is the definition of an average. I believe you must have seen this in your other courses, that you average in the dimension and then divide by the distance, and that's what how you define the average. So let's say we have del square t by del x square plus del square t by del z square equal to 0, right? And then now we say integrate in x, right? So this becomes del t by del x 0 to w, as this becomes del square t by del z square dx 0 to w. So I directly integrated this term. I hope this makes sense. And I hope this also is clear that t dx 0 to w is t bar w from this formula, right? So I've just multiplied w on the other side. So this implies that here, and so let me just go slow. Maybe it's going a bit fast. So del t by del x at w is minus q by k. So minus q by k, right? And the other is 0 because of symmetry, plus del square by del z square of t bar into w. And that's because of this factor, right? So I'm basically integrating with respect to x, t, and limit 0 to w, and that's t bar w. Or finally, this implies that del square t bar by del z square is q by kw. Okay, q by kw. And the reason we went through this exercise, and the boundary conditions here are also obvious, t bar is equal to 0 is t naught is minus k del t bar by del z at z equal to L is h into t bar minus t infinity. I hope that you are able to see now the difference that starts to come in. So now, first note, if q is 0, we get back to the same equation which we had in the scenario 2, when we said it's insulated. Now it's a constant flux. It's a constant flux. By defining this average temperature, we are able to find still a 1D equation with boundary conditions, but there is a dependence in the other direction. Just that we are ignoring it, we are averaging it out. In this problem, the scenario 2, it is exactly 1D. There cannot be any dependence in the x direction, whereas scenario 1 was, there was a dependence, but it was very mild. In the scenario 3, there can be even a large dependence. If q is very large, we can expect that there will be a very large gradient in the x direction, but we can average it out through this integration. So basically, I've described three cases: approximately 1D, approximately 1D, right? Then I described exactly 1D, 1D, and then is averaged out 1D. Okay. And now finally, I like to close this video by going back to scenario 1. And rather than doing a shell balance, I want to basically approach this problem like I approached scenario 3, where I did describe this average T bar. Okay. So let's go back to scenario 1. Scenario 1, right? So we will get del square T by del x square plus del square T by del z square is equal to 0. Okay. Now integrate in x again. Integrate in x. So you get del t by del x. Okay. 0 to w plus, we have discussed this will be del square t bar by del z square times w. Okay. I'm just using this same term, exact same term here. Okay. To 0. Now note that for me to be able to write and for me to write an exact ordinary differential equation in t bar, I need to evaluate dt by dx, del t by del x, and the boundary condition for scenario 1 was del t by del x at x equal to w is this. Okay, so this becomes h into t minus t infinity minus h into t minus t infinity by k, right? This is the value of del t by del x, but t here is the temperature at the wall at tw, right? And plus d square t bar by dz square times w is equal to 0. Now for me to be able to use this to be able to use an equation, I need to know what is the temperature at the wall. But I can only know the temperature at the wall if I do the full problem, right? It's a 2D problem, I don't know the temperature at the wall. But because of the approximation of HW by K, through the order of magnitude of analysis, we said the temperature at the wall will be the temperature at any place at the same Z. So in a sense, we basically through that approximation can replace this by T bar, right? And that's why this was if you allow that, that's when you get the equation which you basically saw in the class 2, WK, right? I can show you that we get the same equation. Uh, Actually, there is a W missing here, so my apologies for that. Okay, so there is a W here. So I hope that this makes sense, that we are able to get to the same equations from different methods. And the main point was there are three different cases: approximately 1D, exactly 1D, and averaged out 1D. So in approximately 1D, the flux is actually dependent on the local temperature. So here it should be T wall, right? T wall. But because of the approximation provided, I can approximate T wall as the temperature at anywhere, as the average temperature essentially. So that's what saves us here. And exactly 1D, there is no flux in that direction, which is the second scenario. And averaged out 1D is when there is a flux, but that flux is constant. It was constant and not dependent on the local temperature. And that's what saves us there. So in general, I just wanted to give you this sort of share this video with you, because with an idea that hopefully this can help you sort of appreciate the few different scenarios. And I hope this video was useful. So please do feel free to reach out to me if there are any questions. And I look forward to seeing you in the next lecture.